Welcome everyone to Webinar Wednesday. Thank you for joining us. Today I'm here with Jeff Sanders from Schrödinger, or Schrödinger. I knew I was going to butcher that. And he is going to present today on surfactant chemistry and the development for consumer packaged goods enhanced by atomic scale simulation. Dr. Sanders received his Ph.D. in biophysics and molecular pharmacology from Thomas Jefferson Medical College. Since joining Schrödinger in 2013, Jeff has served several roles in both the scientific and technical aspects of computational chemistry software. He is currently an associate principal scientist in the Materials Science division, focusing on physics-based simulations in consumer packaged goods applications. Please write any questions you might have for our presenter into the question section on your control panel, and those will be addressed at the conclusion of the webinar. And with that, I will turn it over to Jeff for the presentation.
Okay, thank you, Amy. So today I'm going to talk about a bunch of different applications, and the overarching theme here will be, using computational chemistry tools that aid in not only understanding surfactant behavior, but also exploring, different surfactant chemistries. And know that this is just a small portion, and I focused on a few things that I think are relevant, mainly in the consumer packaged good realm, but by no means is that, very narrow scope. The same principles apply. I always refer the physics stays the same. It's just what are the pieces of information that you're after. And sometimes the same simulation can mean two different things to two different people. But the value is always there. So just because, you may not see your favorite surfactant or exactly what you're looking for, know that, this is just a few features and understanding some basic concepts, and that there are a lot more things, that we can do with computational chemistry software and the tools available. So, what we're focusing on really is, how do we use CompChem tools to understand surfactant chemistry, and if we're developing new formulations or trying to rationalize behavior for something you see in a lab or a way of products behaving, and how does that add to your R&D department? How does that help your understanding and aid, or is it just something else that you just it's another tool in the lab or another technique that you use, like some data science tools? So before I jump right in, just setting the stage, I'm sure most of the audience here are well familiar with the applications for surfactants, the different types of, utilities, wetting of surfaces, controlling phase behavior in materials, dispersion, or if you're, controlling foam, either preventing it or, aiding in the formation, depending on what the application is. And so this, represents one chemical space, one set of tools, right? So surfactants that cover a large range of application areas. And sometimes they're doing, one thing in foam prevention's, a really good example. Some different types of surfactants are going to prevent foams. Some are going to, promote foam formation. So, there's a lot of different ways that they can be applied, and depending on, what you're after, what physical properties or overall properties in your food product, in your textile or cosmetics, or some larger chemical lubricant, it's going to vary, but there are a whole host of application areas. And so, to reference those that aren't familiar with, molecular simulation or have heard about simulations in general, you'll usually see someone present, some time and length scales. So understanding, what are the sizes and what are the, the times at which the simulation techniques are capable, and what they're, rooted in based upon the level of theory. And really, the more rigorous, the more high level theory you go, the smaller the size and the shorter the time scale. And so what I'm going to focus on are really the atomistic properties today, But ComChem is also very good at looking at electronic properties, which are based on, quantum mechanics methods and solving Schrödinger's equation. And that gives you a lot of electronic properties. Atomistic, where you're looking more at morphological and also some, some bulk physical chemical properties, but know that you're right on the order of nanometers. In cases where you can coarse grain things, or you can do some sort of Monte Carlo based methods, you can get to larger scales. So things that might look like a representative volume element, if you do continuum mechanics, that might be, of interest to you. And then, what I would say the bulk of simulations that are done in this area are usually at the continuum level. So finite element FEA or multiphysics models. Those are going to be, whole potato chip here, as the illustrated example, but those are much larger kind, those are on the order of, micrometers to meters, whereas, on the electronic atomistic, we're talking angstroms or nanometers, and maybe if you get above nanometers, you're really lucky with a really coarse grained mesoscale simulation. But that doesn't mean that at each stage there isn't value, and also that some of the information at one stage can be fed up. So, the ultimate goal of multi-scale modeling is one day I can run a QM simulation at the electronic level, get some properties, feed it in atomistic, which is what we do currently for a lot of different types of simulation techniques. And then that MD simulation gives me some information. I can take that, whether it's the structure or some other parameter, feed that into a larger scale, and then eventually the real final bridge that needs to be connected is getting mesoscale up to continuum, and that's an ongoing effort. But maybe in the next 10 years, it will become something that's more routine, whereas now there's usually very few applications and they're tangentially, providing outputs of one scale into the next. But know that, you do get useful information at each level. And ultimately, one day, the chain of simulations and going up the scales or back down the scales will be something that one day will be commonplace. But we're not there yet. That doesn't mean we can't get useful information. So that's all well and good, but how does that apply to something like a food product? Just as an example. So I can talk in nanometers or micrometers and angstroms, but if you're not used to seeing them, then you have no idea what that means. So, to give you an idea of, what pieces or the size scales are amenable to something like MD, we're talking about, modeling hundreds or thousands of carbohydrate polymers, smaller carbohydrate polymers, not something like a full chain amylose, which might have, 10,000 plus repeat units, sugar repeat units. We're getting to the idea of vesicles, maybe some micelles or aggregate behavior. But things like multi-layer emulsions are still very difficult. We're working on that, and actually I'm going to talk about how you can start simulating some droplets, and that can maybe give you some information that you can relate back to experiment, or at least a morphological understanding of how it behaves in the phase separation behavior. But know that for the most part, atomistic simulation is really operating in the individual elements, ions, water, flavor molecules, individual proteins, protein aggregates, up to, multiple carbohydrates and mixing them together. Then maybe some very small scale multi-layered emulsions, but foams and food powders and final products are still beyond the scope, and that's something where, multi-physics simulations are still going to be the primary tool that you go to. So not to bog down with too many equations or too much physics, but just understanding, at the quantum mechanics level and the molecular mechanics or MD level, what are we treating atoms, what's our model, right? How are we treating things, and what are some of the assumptions that we're making? So, right, we're going to treat atoms as charged mass points that are connected by bonds. And at the MD level, those bonds are going to be springs, and they're going to behave harmonically. And, that's very simple, but pretty accurate estimation for a lot of simulation, has been for years. And, the information we get from QM is really going to give us a atomistic force field, which is going to be representative of the forces, the bond angles, dihedrals, torsions, the van der Waals, how big an atom looks, and also its electronic properties. So, understand that if we're talking about a QM simulation, which I'm not going to today, but we're talking about systems described by wave function, Schrödinger's equation, and then that's how the dynamics are governed. But if we're talking at atomistic scale, we're really looking at atomic positions and their momenta, and we're using, Newton's second laws of motion to describe the behavior of these systems. And since I mentioned force fields, it's worth, illustrating out that this is how you actually calculate this. So when you see all these simulations, know that, what we're doing is we're solving, this equation, this potential, and the gradient in this potential in a time-dependent manner for all of the thousands or hundreds of thousands, and in some cases, millions of atoms. And those computations can be very exhaustive because you have to do this at very, very short time intervals. And so to run, we'll see an example of a 1 nanosecond simulation, which you might say is extremely short. That takes a million accumulations of integrating this equation based on Newton's motions. So years ago, you would be very limited in what the size and scale of the system are, but with advanced technology and computers, GPU computing, we're able to simulate hundreds, if not over 1,000 nanoseconds a day, which 10 years ago, and when I was in grad school, you'd be lucky if you get 2 nanoseconds a day. Now, sometimes I get 500. So as the technology scales, so does the, not only the size and scales of which we can run these simulations, but also the applications. And so, speaking of applications, one of the simplest first starting, things you might hear when you talk about surfactants and MD, molecular dynamics, or, atomistic simulations is, how do things assemble, and are the time scales, the kinetics of assembly of something like a microemulsion, and is this amenable to this scale of simulation? And so, just talking about very basic, and this is something you'll see in any textbook, we talk about water-oil emulsions or oil-water emulsion. What's the continuous phase? What's the droplet phase? Or in the case of a bicontinuous emulsion, where you have two continuous phases that are separated by your surfactants, that's going to be controlled not only by the the amphiphilic nature of the surfactant molecule and any co-surfactants, but also what's your solvent? Is it water? What's your oil? Whether it's another solvent or whether it's actually a flavor molecule that you care about, or an oil that you're trying to create a dispersion for. And so understanding not only how these emulsions interact and how they're formed, but also what's the relative orientation of my surfactants, my co-surfactants. If I have multi-layered surfactants, what does that look like? And that's something where MD simulation actually lends itself to being able to look at these type of geometric or morphological features. And so just a simple example to orient us is tilt and rotation angles of a surfactant. So if you have maybe a detergent and it's a simple layering, or maybe it keeps water from absorbing into your jacket, perhaps if it's a single layer, it's going to orient itself. And so depending on whether the surface is hydrophobic or hydrophilic is going to depend whether the head or the tail is oriented. And these orientation angles, how these things line up on the surface, are going to be very important for how efficient they are at keeping water or oils or removing dirt from a surface, or creating that bicontinuous microemulsion. And the nice thing about MD simulations is that we know the positions of all the atoms, we know how they're oriented, so we can calculate things like tilt angle rotations relative to a surface. So we can see, if you change something like temperature, how does that affect the relative orientation, the tilt angles of the surfactants at a surface? And so, again, a very simple example is looking at maybe an SDS bilayer, right? So now we're built a model where we've pre-built a layer of SDS molecules and then water and space separated, and we can look at what is the distribution of the tilt angle and the rotation angles. We can see it's pretty well distributed. This forms a nice bilayer. It might change or evolve over time if we're looking at stability or evolution, or if we've added something else into the system. But we can get this information, and that's all well and nice, but maybe we want to look at non-symmetric angles because symmetric are nice and uniform. And so in this case, we can see that there's a distribution that's bimodal. You have two different arrays of tilt angles, and it might slightly change your rotation angle. we go even further, we want to look at what's the temperature dependent. Maybe you have a surfactant that works really well at room temperature, but 150 Kelvin is very cold. I wouldn't necessarily use that as an example, but just as an illustration, you can change the temperature and you can look at, okay, what are the differences in how these molecules are aligned relative to, a plane, a surface, and, how sensitive are they to changes in temperature? And so that might give you some additional insight over if you have a food product or you have some surface edible coating and you need to freeze your fruits or vegetables for some reason, and what is that going to do? Are the tilt angles going to change, or is this going to fall apart? So these are simple simulations that you can run that give you some idea of how well are your surfactants behaving at the surface, are they orienting, and how does that orientation change, whether it's a change in temperature or pressure, or if you add water, or if you create an interface where there's no solvent and you're now at an air, you're exposing it to air. And so that's a really great example of, what one type of information you can get out of a simulation. But let's talk about maybe some more specific examples. So I picked Tween or polysorbate 80 as an example to walk through, because there's some really good studies, scientific literature out there that I'll go over. And it's also a really versatile emulsifier surfactant that's used in ice cream, soaps and cosmetics, and it's also used in oil recovery or dispersions, and it is also something that's used in things like vaccines and some excipients for pharmaceutical formulations. So it's widespread, it's common, and there are companies that sell lots and lots of it. So if it's there and we want to study what's the behavior of simple formulations of Tween or more complicated, that might be something that we could do with simulation. We can look at things like maybe a dispersing solvent-free emulsion. So if you wanted to add two emulsifiers, so Tween 80 and then commonly occurring lecithin, and then seeing how well it can sequester oil from a water solution. And so this is based on a publication from a couple years ago, and trying to recreate what they've done experimentally with MD, because they're able to see how well the emulsion behaves, what's the relative stability, what's the clarity of the solution, does it cream, does it precipitate, but they're not necessarily able to understand at a really small scale what's going on. And sometimes experimental techniques have limits, and the simulation can really add to understanding or rationalizing why one concentration might precipitate versus one that doesn't, and it's a slight change. So I'll go back to a simple bilayer again. This is a very simple example, but it allows us to not only look at like a tilt angle, but also where is my solvent? Is my solvent interpenetrating my my bilayer, or my my micelle, or maybe even a liposome if you're forming them. Since we know where all the atoms are, we know what type they are, we can look at things like density. And so this is a really simple example of showing that as you take slices of this system, and we're talking about going vertical here, you see that the water is clearly phase separated from the polysorbate 80, and that this is relatively stable. So that's really easy and very simple, and somewhat something we already understand through years and years of working with surfactants. But what if we wanted to break down and look at, okay, so I know that they're phase separated, but is it orienting itself appropriately? Is the tail face, is it a reverse micelle or a normal micelle? And so now I can look at the ring structure, or I can look at some of the terminal hydroxyl groups or the hydrocarbon tail, and I can look at the density distribution here. And what I would expect is that depending on the orientation, in this case in water, it should be the tails are on the inner side, it's a normal micelle, and that the head groups, whether it's the terminal hydroxyls or the ring, should be relatively close together. And so that takes it a step further from just saying, okay, is it phase separated? Well, what part of my molecule is where? And you can actually do more interesting calculations of looking at the distribution and even packing density to compare against theoretical packing efficiencies for micelles depending on the chemistry. And then we can look at, even more interesting systems, going back to that oil dispersion example, where we're looking at, a combination of two different emulsifiers in this case. And so, this is a very short simulation. This is probably a couple 100,000 atoms. So, I could have run this longer, but just to illustrate a point, again, the water is not, present. There's really no interpenetration of the water for the most part. This is an elongated micelle, so there will be, on the top and the bottom, on the sides, there'll be some water. But more interestingly, how well distributed are my two, surfactant and co-surfactant? Are they equally distributed? Which you'd say that, yes, slightly. I mean, you'd have to correct for density here if you wanted to look at a population, but you see that there, maybe there's a bit more towards the center, less of them might be shifting since it's a slight, it's got two tails, right? So it's may not be able to pack as well efficiently as the polysorbate. But we can track these, and we can also calculate the diffusion if we wanted to, either if we're forming a micelle or within a micelle, we can also track that information. And so since, some of the coolest parts of simulations are the movies, where we get all of our data from, it's worth pointing out, here's an emulsion that I did not preform this. I actually simulated just the decking by itself and then added the surfactants around it. But this was after, at least 100 nanoseconds of simulation, watching the micelle, which is now already formed, and seeing, is this the relative right sizing? This is actually a little smaller compared to what's seen experimentally for particle sizes. So you can still somewhat see the decking kind of poking out, and that's probably because I need to add more surfactants in order for it to reach a particle size that would completely encapsulate it. But nonetheless, we're able to see that, right, the decane obviously does not want to, pop out and go into the solvent phase, the water phase. So, the emulsifiers in it surround it and they're going to move around. And so looking at not only the distribution, but also the dynamics and measuring things like, radial distribution functions for either different head groups, looking at what's interacting. If there was a salt solution or if there was something else, we can break those apart and we can look at where is everything localizing. And here afterwards, I'm just looking at, this is a relatively stable micelle. And then if I want to take, slice it in half and look at what's the distribution without just doing the density, I can remove half those atoms and I can look and see, are all of my decking inside? And yes, they are, as I would expect. And you can also start to think about if there was another co-solvent in here, in some cases on larger organic sites, sometimes you can have crystallization of molecules, not necessarily in a micelle itself, but if it's within a liposome. So, that even extends the ability of looking at morphological behavior within the emulsion, not just the overall size, shape or stability in solvent, but also looking at the individual components and their relative orientations and how are they behaving. Okay, so I'm going to jump to a slightly different example, but along the same theme is looking at, food emulsions. So maybe a beverage emulsion where you're trying to add a healthy ingredient, not just more sugar, but something like a flavor compound, something that maybe if it's within the solvent phase is miscible and it will precipitate or it will separate, the entire emulsion, or it, reacts. So in some cases, if you have multiple flavor oils or health-related compounds, they'll react if they're together. So having, emulsions that are well separated phases help keep the stability. And, and depending on what type of environmental stress, whether temperature changes, pH changes, how does that affect, how stable the emulsion is? So I'm going to use again polysorbate AB, Tween 80, and beta carotene, which is an essential nutrient. And we can build, again, emulsions, and we can look and see, how does that actually look and what's the morphology. So I'm going to show you a movie again, too, because it's actually something that was pre-built. I didn't, make a builder to build a perfect micelle, but I just added these in a water box and watched them, equilibrate over a couple 100 nanoseconds. In this case, I'm recording 50 nanoseconds at room temperature. But again, I can look at the densities, and, what I expect is that for the, the oil phase, the beta carotene, I would expect it's going to be in the center and that you're going to see more of a density of my emulsifier around it. And that maybe it's going to, if things are forming stable micelle, continuous if it's elongated, or worm-like, I should see this behavior. So again, I'm going to another simulation, since it's worth noting that if you look at this early on, you see some of the, the beta carotenes are not part of the larger group, so they're somewhat separated, but still trying to form a stable emulsion. And so very early in the simulation, you'll see this on the right are separated, but as the dynamics progress, as the system evolves, you see the relative rearrangement, and it actually starts to form a more stable micelle, again, with the beta carotene going to the center, and also, the morphology changes. And there are also other experimental techniques like small angle X-ray scattering, where you can look at the relative size and the d-spacing group for how big are, for say, one of the phases. And that's something we'll talk about in a second, but this is again to give you an example of, this is a simple two-component emulsion. You can imagine adding multiple layers. Maybe you had another co-surfactant or another layer of something on top of it. And these can easily be built, and we can run the dynamics and start calculating. So this is now forming a really nice stable. All the beta carotenes are more or less on the core. And that was, a very short simulation. You could run these a lot longer, and you could add multiple ones, and you could start, looking at aggregation sizes. Again, something I'll talk about a little bit more towards the end. I mentioned that everything up until this point has been, atomistic, and then there's also coarse-grained in there. And so what is coarse-grained? And, there's another problem where this is actually well suited to discuss, a higher length scale getting towards a mesoscale simulation. So, sodium di-2-ethylhexyl sulfosuccinate, NaOT, for short, is it's used in coalesce as a soul softener, and it has a few other applications. It's pretty well known. You can find it on there on your shelf. And understanding the morphology behavior really affects, this surfactant and its ability to form different types of micelle shapes. And this is a bicontinuous emulsion. So depending on if you're looking at, a ternary phase diagram of, your three different ingredients, right? So if you have heptane, water, and your NaOT, depending on the relative concentrations of each one, you're going to form a different type of morphology, a different type of micelle, and that's going to be really important. So this is based off of a paper that was published 6 years ago in Soft Matter, where if you look at that that line where they've labeled A through M, those are well-known phases that they're able to identify, and can we use atomistic or coarse-grained simulation to recreate those? And depending on how much change in either water or heptane, can we reproduce the phase behavior? Because that, rather than running all the experiments to get all those points along this phase diagram, you can imagine running simulations either along the line of interest or varying points, and saving yourself a lot of time and energy. And so I mentioned we're going to coarse grain. So, what is coarse grain? How does that compare to, an all atom, everything I've talked about up until this point? So if we take something like lecithin, and we look at an all atom, right, we're describing all of the atoms as balls, and they're connected to springs for bonds. And really what a coarse grain model is the same thing, except rather than mapping, one ball to one atom, we're now going to take one bead. It's going to represent multiple atoms. And then we're going to have to come up with a new force field that describes the behavior, because right now each bead is, not just the sum of its individual atoms and their bonds, but they're going to have a behavior, and we're going to need to make sure that those particles behave overall, whether it's a density or it's a morphological, property that we can measure with simulation. Do those behave properly, and can we come up with a consistent force field to describe that? Why we bother doing that, as I mentioned earlier, if you want to get to mesoscale, you want to get beyond just simple couple nanometers, and you want to get to tens and maybe 100 nanometers, pushing towards, micrometers, not quite there yet, and longer time scales, going multiple microseconds. You need to use the coarse grain force field. Atomistics will just brute force take you months on months to run a single simulation. And so just to give you an idea of, how well coarse grain can perform in, in morphologies, right? So earlier we looked at things that were relatively preformed or sort of pre-packed, and you see some minor evolution, but those are relatively stable micelles. You don't see them forming. This is a system of over 10,000 lecithin molecules, and starting with a random orientation, can we form first like micellar bodies and then overall something like a liposome? This is something that with Atomistic MD you could never do, or at least it would take you longer than you would want to be able, and that might not be interesting for the size or the scale of the problem you're working with. So if we want to get to more realistic surfactant problems, emulsions, multi-layered emulsions, liposome type problems, nanoparticle loading, coarse grain is the way to go. And so, without showing that movie again, we can talk about, again, NaOT, this time describing it with a coarse grain model, applying beads just for, the different hydrocarbon tails versus the polar head, and then maybe incorporating the salt within, the head itself. And then, water models are there, and then heptane's pretty simple. So we can build a model, and then we can also vary the water concentration to try and reproduce the behavior of, as you go up in the ternary phase diagram of your water concentration, that changes the behavior. And so what we see here is as we add in 5% increments percent water content, we go through something that's somewhat dispersed to having larger and larger water channel sizes, up until the point where you get to about 40 or 45 or 50% water, and it's at this point a it's a continuous emulsion. And so this is all interesting, great morphology, but can we compare this against something like small angle X-ray scattering curves? So with simulation, again, we can predict this. We can calculate them. We can calculate the spacing, right, which as we add water content should get larger and larger since we have a larger solvent channel there. And then we can start to either make, in some cases, you can quantitatively compare this to experimentally determined Sachs curves, or you can relatively qualitatively say, does it get larger or smaller? In this case, this actually matches pretty well the experimental behavior that's seen. Okay, so that's all types of atomistic simulations and coarse grain that tell you a lot of things about morphology, and are really good because they fit well within the time and length scales. Sometimes, we run into situations where physics-based simulation just won't work. And a simple example, and it's kind of the fringe case here, though surfactants are involved in dealing with the issue, is flammability. Flammability is a common example. It's not something you can predict with simulation. It's very hard to do. And so can we, switch to other methods like machine learning, the hot topic of say the past few years, and now AI. And can we use chemical information? What does a surfactant look like? What's the chemistry? And maybe use it to build a a statistical model with some other properties. And so just to describe how machine learning models and chemistry have worked, and this is chemical informatics. This has been around for years. This is nothing new. Some of the newer methods are interesting, and I'll point that out with deep chem, but multiple linear regression, support vector machines, those have all been around for years and are something that chemical informatics practitioners have been using. We built a tool that allow you to, if you're not an expert, I know I didn't get a Ph.D. in chemical informatics, I barely used it for years, understanding what type of model to use, depending on the data I'm providing it, not just whether it's categorical or continuous data, but the quality, what type of descriptors, do I have a ton of experimental information about all of these classes of molecules that I'm using, can I incorporate that in the model? I have no idea. People spend years and years becoming experts. So some of the people internally said, well, why don't we just generate all the models possible? So there's many different types of molecular descriptors, and something that's an example of an easy descriptor is number of rotatable bonds, number of hydrogen bond donors and acceptors, charge groups, hydrophobicity, or any other property that you might have measured in the lab. We can build tons and tons of models. We can score the models, and then we can tell you how well they behave. And then in some cases, if we're using property-based models that are based upon fingerprints of the fragments of the molecules, can we show you, and in the lower right-hand corner is a good illustration of what properties are contributing based upon a chemical fragment, either in a positive or negative way to whatever model you're trained or built. And so I'll give you a simple example in a minute. And then, with the newer machine learning and, models, right, if you're looking at something like graph-based deconvolution neural networks, you could take those traditional methods I just talked about, and then you can also train things depending on the number of data that you have to build a new machine learn-based model. You need a lot of data for this, usually over thousands of data points, over 1,000. But this can now be done. It doesn't require a machine learning expert in-house. We actually have a tool. It's a Deep Chem, we're a commercial sponsor. It's freely developed and it's integrated within our software now that allows you to train a model for something like critical micelle concentration or something like solubility. So this is a simple example where we took thousands of data points for organic molecules, looked at what are the traditional ways of predicting something like solubility, and how well does a a traditional model look, and you get a pretty decent R-square between the training set, test set, everything looks fine. But if we actually use a machine learn method, are we able to increase the accuracy of our model depending on whether it's trained for a long time or how many data points we use? So in some cases, machine learning can really help and aid in building better models. Always important to point out that it really depends on the domain of applicability. We do have the ability to identify if you throw in data that's well outside of the chemical space that's defined by the majority of the molecules and individual rows of data is really compatible or it's outside. But it does give you a slight advantage in some cases. So, a really simple example, since there's a lot of different ways we can do this, is calculating critical micelle concentration. You may be able to do this with simulation for really, really large micelle particle sizes. You may not be able to get there in the, in the amount of time that, even a coarse grain model will allow you. So can we take, the chemistry of like sugar-based surfactants, polyol-based surfactants, and can we, if we know the critical micelle concentration for a bunch of them, can we, take those and can we build a model? Well, yes, we can. The chemical space is pretty well defined here, and we can do multiple linear regression. We actually have 6 independent descriptors in this case, and this was a model that you can build in like 2 minutes. The hardest part is usually formatting all of the data and anything you've measured, generating the descriptors, and building the models. Like the model's usually the fast part. So this is, always an alternative when we run out of, our tool set for running physics-based simulation. This is where we usually say, okay, let's try informatics-based models, provided the chemical space is well defined, and there are checks to put in early to make sure that your data sets actually give you a reliable model. All right, so the last thing I'm going to focus on, I realize we're almost at the 40-minute mark, is protein-based emulsions and surfactants. So the idea that we have traditional surfactants, pretty standard. Some are made naturally, some are synthetically made. That can be expensive, or it can be less than environmentally friendly. And are there alternatives that nature provides in some cases that we can use, and can they have some advantages over other behavior, or if we're worried about nutritional or health conscious, as the markets move in that direction, provided something that's based of 20 amino acids that we all know well, is that something that's an alternative, and do they display the same properties, and can we model those with simulation really? So again, we'll talk about food emulsion foam, so we're not going to be modeling the air in this case, although there are ways of doing it, and feel free to ask afterwards. But understanding, right, something like whipped cream, then the macroscopic, we're looking at 10 millimeters, and then you have your air bubbles and your water and your surfactants in between, and those are on the 2 micrometer and then the molecular scale. So if we really want to look, in this case, either looking at in the water side or even the air-water interface, that can be done. I'm just going to show you water interface, but know that it can, you can expand it. And one of the most common, biosurfactant proteins are hydrophobins. They're used for protein emulsion and foam stabilizers. They're very cheap to make. They occur naturally in filamentous fungi. They're used for, breathing and also for, in some cases, growth. They're well conserved, really small protein. The application areas are immense. There's tons and tons. Pharmaceutical side, consumer packaged goods side. Know that they have a highly amphiphilic surface. They display surfactant-like properties. And they are used in some cases for emulsifiers, anti-wetting surface coatings, and then a ton of biomedical applications. These could be an alternative, as opposed to traditional amphiphilic surfactant molecules. And so when we talk about proteins, now we're talking about larger molecules. Can we identify hydrophobic patches on them if we're trying to engineer or design a slightly better molecule? Maybe what nature gave us is not quite good enough, or there's some other processing property we're trying to get around. And so there are ways of calculating aggregation scores, or aggregation from regions on a protein, that will tell you, what's the contribution based upon the atoms, the individual residues, and how much is that a propensity to aggregate. And this is based on, again, internal work, focusing on building a tool that allows you to very quickly predict this. And here's an example of why you would want to calculate this. And this is a a protein that they've used on the life science side, and they're looking at expression, and so they're trying to make this thing. And if you're trying to make it in large batches, you don't want this to aggregate, because then it might not be refoldable, it might be unusable. And so you might need to engineer, make some mutations on, in this case, a particular loop of the adnectin. And can we, rather than go through the really expensive, doing the mutational, in your genes, making sure that you have your vectors are inserted well and that your expression systems are optimized. Can we predict this aggregation score, and what changes do you make? How's that's going to affect it? And actually, the predictions are, again, we're rank ordering here. We may not be, absolute, but we're able to differentiate between mutations that increase solubility and decrease the aggregation propensity. And so how do we tie that back right to hydrophobins? And hydrophobins are pretty well, they're mapped out. They have this this hydrophobic patch on the bottom and this positive patch on the top. And that that's where the orientation of the surfactants of the hydrophobic patch might orient itself relative to air or a solvent, depending on which class of hydrophobins. This is a class 2. And so we can break down, based upon each individual amino acid, what are the relative contributions to the hydrophobic contribution or the aggregation propensity. And so a few charged residues actually sit around that 40 to 50 residue index range. And if you mutate those, you can very much alter not only the oligomer, the aggregation, how do these hydrophobins self-organize at the interface, but also their relative propensity to behave like a particular surfactant. So, this is just a simple illustrating that, the ag score is very low, around 40 to 50. That's very important. Those are residues that have been identified through other experimental works to show that, you definitely don't want to change those, because they will change your partitioning coefficients, your loading capacity, and also your oligomerization states independently. And that, if we go, and I don't have the data, it's actually fresh off, if you do some of these mutations, you'll see that some of the conserved residues, or the residues that don't pop up on the ag score, have really, really high contributions to keeping the ag score down. And if you were to go mutate those, which you can do computationally, it drives them up very quickly. The other nice thing about it is we can look this at different classes. So if you were trying to select a different biosurfactant, where are the patches, what's the relative score? So the score may tell you overall whether things aggregate or not, or relative wear on the surface if you're trying to make some modulations, or if you're trying to select the different type of co-solvents or co-surfactants. And if you can compare different types, ones that have higher aggregation propensities, I mentioned earlier, that 40 to 50 range or close to there, depending on how much you shift the relative sequences, can have an important contribution to the overall aggregation. So something that has lower aggregation is going to have a different profile, even though the hydrophobic context and contribution might remain relatively the same or look the same. So these are all useful tools. They're more on the the sort of biosurfactant protein engineering side, but they're very useful for looking at aggregation propensities, and then you can go ahead and apply this whole host. And this is, I think, almost every crystal structure known for hydrophobins, comparing the different aggregation scores, and you can break this down into contributions on the individual amino acid level. And then you can also start comparing different ones, whether you're selecting to add in a particular foam or an emulsion for any sort of application, which one you would choose. Next, if you want to actually predict aggregation, it's something that can be done. These are actually pretty small proteins. They're very globular, so that allows us to do a lot of interesting simulation things. And I'm hinting at coarse grain here, but we could set up 12 individual molecules in a box. Usually most simulations you see with proteins are maybe 1 to 2, and we can run this for a long time, and we can start to look at what's the aggregation behavior, how are they coming together. And I mentioned earlier there are more advanced tools. We have ways of calculating what's the radius of gyration of the clusters, or the largest cluster, and how are they aggregating, right? So if there's 12 molecules and they're all going to form one larger aggregate, what's the relative orientation and how long does that take? So this kinetics can start to really think about looking, at least in a small scale, in a semi-dilute environment, how to predict kinetics. And they've done this for micelles with MD, and using aggregates, they're able to predict, the micelle formation kinetics, right? And then the packing efficiency. You can do a lot of this with just knowing the radius of gyration, and also the relative aggregation size and number of aggregates in a system, depending on how many surfactants, co-surfactants are in there. And then, that brings us back again to looking at larger changes with coarse grains. So maybe we want to add 20 plus proteins in there, and we want to add a co-surfactant, and again, lecithin, and we want to look at self-assembly. And this is again millions and millions of atoms if we were going to do it at the MD all atom scale. But at coarse grain, it knocks it down to 100, maybe 100,000 bead particles. And we're able to do this, in microseconds a day. So this is a simulation I ran overnight, starting with just, random orientations of, my hydrophobin and also my co-surfactant. And by by 1 microsecond, I can see small micelles with a lecithin and bicell form and bridging with the hydrophobin. So they're able to actually bridge independent smaller micelles. And, I could do more actual calculation of micelle size, density distributions, radius of gyration for the individuals, to determine not just the orientation and the relative alignment of individual protein molecules, but also how are they interfacing with the micellar bodies. Is there a limit if I were to start varying the concentration of either the protein or the co-surfactant lecithin? How does that change micellar size? Does that change the way in which the hydrophobins orient themselves? And so this is kind of where we're really pushing at. And ideally, then you could take this, and some of my colleagues internally have worked on for the case of really low viscosity, and we're talking 100 to 200 centipoids. We can actually get shear viscosity values for systems similar to this. We have a publication out, and a few other examples of looking at very basic protein solutions, mostly dilute, but calculating relative viscosity changes. You're not going to get above a few hundred centipoids, because then the relaxation times are well beyond the scale. But as we keep pushing and pushing, most MD simulations now, if we talk about viscosity, are 40 to 50 centipoids, and we've been able to push with coarse grain up to maybe several hundred centipoids, maybe 300 I think might be the max currently. So that now opens us to more rheological properties. Things like glass transition temperatures are easily predicted for solid materials or things that have low water content. But if we can get shear viscosity, that really starts talking about processing properties that we care about beyond just morphological, which is what I spent the majority of the time talking about. We can really look at what are some physical property behavior and changes. And we can do all this without running all the costly experiments. I think I've kind of undersold that here, is that this doesn't replace every experiment, but rather than run 50 on 50 different surfactants, you may be able to run the simulation on 50 and then funnel it down to 10 and make a selection based upon those without having to run. And you can run these simulations. Most of these I ran and built in a day and a half. So they're not something that takes a month to do, which is important for impacting high profile or mission critical projects. So with that, I'm stop and ask for questions. I know it's a lot, but these are just a few of the capabilities. There's certainly other things I haven't talked about, like um, degradation pathways of individual molecules, redox and oxidation potentials for lipids, something we're focusing on. That's all QM level. It's a lot more single molecule, but for shelf life stability and reactivity purposes, those are other questions that we can think about answering at the individual molecule level. But also, something that we're actively interested in, and something that we've seen a lot of our customers express interest in beyond just, looking at morphology of a micelle or, complicated emulsions. So yeah, so I'll stop there.
Hey, thank you so much for the presentation. And it seems that we already have quite a few questions posed. Thank you, everyone. Should you have additional questions, please write those in the question box, and those will be addressed. But I'll go ahead and get started with some of those that have already been posed. So our first question is, are the MD calculations, and this is a two-part question, are done by feeding some DFT data? And if yes, what are the parameters taked from DFT and plugged into the MD calculation?
Okay, so perfect question. So all of MD force fields are built on usually a combination of DFT for the electronics, and then van der Waals are usually from experimental data. So our force field takes DFT, and actually, depending on if the chemistry is covered, we actually fit the DFT on the fly. In the case of the DFE, all you really need is the chemistry, right? So the molecule, and unless you're really, really far away from a conformation that's, the relative low energy minimum. So starting with a flat 2D structure may not be the best because you can run into chirality issues. You can actually just run the DFT. Thankfully, there's been a lot of work on building surfactant force fields. So we've done work, out of Harvard. Charm is its own, lipid force field. And so those parameters are already there. So if you're working with something that's already characterized, you can just plug in the number of molecules in your box. But we also actually allow you to have tools to do the force field fitting if you're missing some parameters for those. And yes, those get fed right into, building your MD system in the force field that's used for the calculations.
Thank you. During the simulations, do you allow the volume of the supercell to relax or keep it fixed?
Yes, so I think every single one of those simulations I showed were NPT, so we keep the particles, the pressure, and temperature fixed, so not the canonical NBT ensemble. I think the only one that was done slightly differently is with the bilayers, you generally run a constant surface area. So an NPAT ensemble, that's just so that you don't deform the bilayer as much. But yes, those are all allow volume fluctuations, and they're all done in 1 atmosphere, but you could change the pressure and go up if you wanted.
Are the shown results in simulations kind of predictions or explaining existing phenomena?
Great question. So a mixture of both. Usually with the small micelles, if it's like a single micelle like polysorbate 80, those are, you can make those micelles very easily. Usually it's explaining, if you have sacks, right? So small molecular scattering, you might know particle size, that, you can compare that. And so that's just what we call that, like either validation or if we're rationalizing. Another case that would extend to that is if you have a co-surfactant and you wanted to look, okay, from sacks the radius of gyration, but you don't know if they're being evenly distributed through the micelle. That's where it's being rationalizing. Informatics or maybe some of the protein engineering stuff is predictive because you don't know, maybe you don't have sacks information. And so now the morphology is really being predicted on the fly, or in your informatics case, the critical micelle concentration is done based upon just chemistry and other experimental, CMC values you've gotten from other systems, and you're maybe throwing a new, slightly modified surfactant at that model to predict CMC values.
Okay. Next question is, most surfactants can be explained by head and tail relationships, but I work with surfactants with elongated heads and multiple tails. Does this significantly complicate your measurements?
It doesn't. The easier analogy is triglycerides, which are not just right. So they can have trident, they can have, multiple different orientations. Those can be well defined and explained through coarse grain MD, and they've actually gotten crystallization for triglycerides pretty well down. It's on the order of microseconds, that transition from amorphous to semi-crystalline or full crystalline. It can be done. The question becomes always, what's the lengths, right? So if you have a really long set of tails and a really long head group, it's gonna affect the speed, but also what's the minimum number of molecules? And so we call that like finite size effects. Sometimes your system's so small that you're missing behavior that would be described by something that's 10x that size. It's going to depend on the chemistry, but there's always, some things where you could build a really large coarse grain system, or you could look at smaller, if you can't simulate the whole micelle, you might be able to simulate a curvature of part of a micelle. And so that people have gotten away with that in the past. So there's definitely ways. It just depends on how long and, what's the overall flexibility of those molecules. But you could, always build it and try with my, position on those things.
Doing MD simulations for these materials is indeed great and exciting, but how to prepare the topology files and details for these SDS surfactants or whatever is being used. Generally, we can create topology files for protein and ligands under 150 to 200 atom size molecules.
Right, so that's the whole force fields coverage problem. One thing that I did not mention and point out is that we have a force field that's based on the OPLS all atom force field that has the largest chemical space coverage that I think we've seen no one else publish that. Usually, as soon as you get beyond nucleic acids and proteins and small sugars, you usually need to do force field fitting, a lot of QM calculations, a lot of fitting, and then refinement. We've actually taken a large portion, like thousands or millions of organic fragments, and run the QM calculations to fit. So we have a large portion of chemical coverage. It's very rare for me to find something that doesn't fit unless you get into metals, which are a whole other problem. But in the case where you're missing a torsion angle, we have tools that allow you to do automated force field fitting, where it will identify missing torsioning angles, and it will run all the QM calculations, and then it will refit and give you the relative errors of what maybe the torsional landscape was before and after, either just from straight QM, the default force field, and the fitted one. So yeah, so we have tools and techniques, not only just the large coverage of force field, but also the ability to do force field fitting or do ESP fitting from QM calculations if you need to do custom charge-based distributions in a variety of cases. You might want to do that. And it's all done within a GUI, so it's mostly automated.
Thank you. How to predict surfactant behavior in personal care products such as foam, speed, viscosity, build, and fragrance solubility.
Okay, those are a lot of questions. I'm gonna the last one first. So the solubility. There's a few ways that you can calculate solubility. There are ways that you look at solubility parameters, Hildebrand and Hansen. We can predict those for single component systems or multi-component systems. And so you look at the distance in Hildebrand or in Hansen space to see whether something might be miscible or not. We also have free energy methods for looking at solubility. So in aqueous solubility, so starting with something that might be amorphous and then transforming that, basically taking it out of the amorphous environment into the solvent environment through, calculating the sublimation energy. We can do it that way. And then there's also some tools for partitioning where you do solvent swapping and you can calculate it. Now that depends well on the size and scale of the molecule because you need to do a lot of exhaustive sampling. But we have at least 2 or 3 physics-based techniques that we can use to look into that. on a per molecule basis. And then if you get into larger formulations, then we can fall back on solubility parameters in comparison to, pristine individual components. Foams are a little tougher. So foams have really low densities, and most of the simulation that I've showed are in the condensed phase. Where we're able to look at, foam, and I've seen probably the best foam simulations to date are usually looking at surfactant orientation, arrangement, and like kinetics at the air, water or solvent interface. So you can build a system where half the box is air, half the box is your solvent, and your surfactants either, randomly in the solvent phase are oriented at that air-water interface or air-solvent interface. And you can look at the relative stability and, lateral diffusion, or if there are things on the surface, how do they absorb? But prediction of a foam is kind of, when you go back to that scale, foams are still outside the scale of what we can do, but we can still look at some of the more microscopic problems at either the interface or some of the solvent continuous phase. And then, so as for viscosity, we can do viscosity on, again, condensed phase things, but we have upper limits of, 200 to 300 centipoise. After that, the simulation times just become so restrictive that it would take us probably years to run a simulation. So the answer isn't no, but it's contextual. And then in the case where we can't, we might be able to get mechanical properties or TG properties that kind of help supplement. When we can't get viscosity, we can go to other rheological properties that help us kind of understand the behavior of the bulk material or, some phase of it.
Okay, thank you for that. And the next question, I did shoot it over to you if you can see it, because I'm sure there's things in here that I will not pronounce correctly. But it's requesting an explanation of the kind of force field used for the simulation for these molecules. Do you see that question?
Yes, right. So the OPLS 3E force fields, is based on the OPLS 2005 with some extra fitting. The publication is available. If you want to email me, I can. That's an ACS journal. I forget which one it's in, but we've published on all of our force field improvements. Our force field is proprietary, the OPLS 3E, so you would not be able to run it under GROMAX or AMBER or CHARM. It's one of our competitive advantages in that, as you well know, it's not easy doing force field fitting, and we've run the last force field fitting project that the force field team did required running millions and millions of Jaguar, so QM calculations on the cloud in a day and a half, and that, there were hundreds of, either tens or hundreds of thousands of computational years used to predict that. So the OPLS 3E force field does not work outside of Desmond, our MD engine within our products.
All right, thank you for that. And the next question is, how accurately does the ML model predict, and it's a multi-part question, don't you think a specific MD simulation-based prediction will be more useful and accurate rather than relying on model? I still think we don't have that much data, and a lot of IFF and buff is there.
Yeah, so right. So my spiel, and I'll keep it real quick, is with whenever you're doing a machine learned model, it's usually a last ditch effort because you can't run a physics-based simulation, and I'm always partial to physics-based simulations since it's my background. The issue is the quality of the data, right? So if you take data from 5 different databases, GRASS, some other stuff, and you're trying to compare disparate descriptors and other information, or even the experimental, right? So your continuous variable that is taken from multiple labs or multiple different people did it. There's always a question of the reliability of the data. I agree that if you can run the simulations, absolutely do it. Especially with CMC, something where usually you can get it directly from MD. There are cases where there are just some properties that are not amenable, and going outside the surfactant realm, spark sensitivity for like high energy materials is not something you can get easily from QM or MD, so they've relied on QSPR, but that's always my fallback, and people are always interested in machine learning. there are other more interesting ways I think you could apply machine learning in this case. And yeah, I would always push for doing the MD first. That's my personal take.
Okay. And a request for discussion on some of the materials available from Schrödinger. Excuse me.
Yeah, so absolutely. So I know that there's no email here. I think Amy, afterwards we can send out to all the attendees, right? I can send contact information if you're interested in specifically this stuff. You can email me, and if there's more information about Schrödinger overall that you're interested in, I can direct you to our account managers who will help set up at least the meeting, get an idea of what you're interested in, and then put you in contact. I'm not the only scientist that works on these things. We have a whole host of them. There's over 150 chemists at Schrödinger with PhDs in that area, and so there's a lot of different people. And depending on what you're interested in, we want to get you in front of the right person so that they don't just take all the questions and have to go back ask someone else. So yeah, more than happy to have any subsequent discussions about this or other areas. Just let us know, and we're happy to reach out.
Perfect. And I will you'll receive a follow-up email with a recording. I'll include that contact information as well as the e-certificate for attendance. So you will receive that in a few days. And there is a follow-up question to that. I'll shoot it over to you, asking about a specific material.
Okay. Yeah, electronic properties. Yes. There's other guys that are not me that are very good at talking electronic properties. So we have things for optoelectronic properties, redox potentials, whole energy electron, so HOMO-LUMO gaps, even charge mobility with kinetic Monte Carlo, bond association energies, reactivity from transition state searches into temperature and pressure correction reaction rates for catalysis, homogeneous. Heterogeneous is a little tougher to do, but we have a whole slew of QM guys that work on that day in and day out that I'd be more than happy to put you in contact with that focus solely on those properties.
Okay, I'm looking through, and I think as we're past the hour, we'll wrap up the Q&A portion here. But again, just to reiterate, you will receive contact information so that you can follow up and be put in touch with the correct people to have further questions answered for you. So thank you so much for the webinar today. It sparked great discussion, and thank you everyone who attended as well as for your participation in the discussion. So thank you so much. I hope everyone has a wonderful rest of your day.
Thank you.